Hey everybody, welcome to virtual algebra class. We are finishing up our unit on the geometry that's on the GED. And why do I call it virtual algebra class? We're talking about geometry because just about all the geometry on the GED is algebra based. So we're going to be looking at another algebraic concept that is applied in the world of geometry. So if you haven't already seen the video on proportions, if you don't know what a proportion is, you're ill prepared for this. I'd go pause this video, I'd go back and watch the proportions class, and then check this one out. But we're going to be doing geometric applications of proportions today. So let's go ahead and tell you something super important. I have a vocab word that you have to understand. There is something known as a similar shape. Now, if we were not a GED class, if I was just your geometry teacher, I would spend lots and lots and lots of time with you talking about similar shapes. We would define a similar shape based on certain characteristics, and we'd spend all this time proving that shapes are similar. Since those types of problems don't come up on the GED, I'm going to kind of gloss over that, but I do want you to understand that similar shapes are shapes whose corresponding sides. So when I say corresponding sides, I mean the ones that are correlated, like length with length and width with width. So a shape whose corresponding sides are in proportion. Now you see why I said that we need to remember the word proportion, because we need to know what a proportion is, because here it comes up. A similar shape is shapes whose corresponding sides are in proportion, meaning that the ratio or fraction between the sides is equivalent. So basically, if I say two sides are similar, you can make fractions out of their sides and the fractions will be equal. There, I said it in plain English. That's what I mean by that. If two shapes are similar, you can make fractions out of their sides and the fractions will be equal. They'll be equivalent. So now let's take a look here at these two rectangles. Now these two rectangles here appear to be similar to me. So we talked about it last class when we talked about being in proportion, and I talked about shrinking down a picture. Now it's actually kind of hard to tell with a rectangle if the two sides are similar. If I had an actual picture in there, like a picture of the Mona Lisa, and I shrunk it down, you would very easily be able to tell just by looking at Dear Mona whether or not my thing was in proportion. Because if Mona's head got all squished down like that, you'd say, oh, you messed up the proportions. Or if her head got all pulled up funny so she looked taller and skinnier than she usually does, you'd say, okay, you're not in proportion. Okay. But when I look at a shape like this, just a rectangle, it can be a lot harder to tell if they're in proportion. You should not visually assume things are in proportion. Rather, you should check. Let's look at an example here. So, I don't know. Let's say that this rectangle, I measured it, which I didn't because I'm super lazy. And it was 15 inches this way, and it was 25 inches this way. Then I came over here and I measured this sucker, and this guy was a 6-inch by 10-inch. And you're wondering, well, are they in proportion? Are these two in proportion? I could tell. If they are in proportion, then the ratio of their sides will be equivalent, meaning that if I make a ratio or a fraction out of the first rectangle's length to width, it should be equal to a fraction that I made out of the second rectangle's length to width, like 6 to 10. Okay, that being said, I said it should be equal. Last class, we learned how to prove if fractions were equal. Does anybody remember how you can know for sure that fractions are equal?
You cross multiply.
Exactly. You cross multiply. So I'll just do a little reminder from last class. If two fractions really are equivalent, then they're cross products, also known as cross multiplying. Cross products are equivalent. Wonderful. So let us check it out here. First, I will grab one cross product. I will do the 15 times the 10. 15 times 10, of course, gives me 150. I apologize for my crappy handwriting. This is because I'm on my PC instead of my tablet. I will switch over shortly. and I get 150. Okay, now let us examine the other cross product. If I multiply in a cross shape, or one numerator times a denominator, and let's do it in a different color, then I'd take this numerator times this denominator, and of course 6 times 25, 6/4, is also, well, 150. So what do you think? Are these two rectangles in proportion?
Yes.
Yes.
Absolutely. They totally are. So it's super nice. We can use this relationship to prove things are in proportion, but that's kind of just like a yes or no question. Like, are they in proportion? Yes or no? Y'all had a 50-50 shot at that anyway, right? What else can we use this for? Just like before, we can use this relationship to find missing sides of similar shapes. If we know that they're similar, we have to know, though. Once we know they're similar, we're guaranteed their cross products are equal. So once we know they're similar, we can use this relationship to find missing sides of similar shapes. So if we know that two shapes are similar, and this is really where we see it come up the most on the GED, we can use proportions to find missing side lengths. Cool. So let's go take a look at some proportion applications. So a lot of times students mix up when to use this similar shape rule and when to use the Pythagorean theorem, because they both find missing sides. So remember the Pythagorean theorem we used when we just had a single right triangle and we knew two sides and we wanted to find the third. Okay, Pythagorean theorem works on one right triangle, on a right triangle.
Right.
This proportions we use when we have two shapes that we know are similar. They're basically like blow up or shrink downs of the same shape. Okay, so looking at 1A here, I guarantee you in my directions that we have similar shapes. It says each of the pairs of figures below is similar. Okay, I guaranteed you it was similar. You don't have to prove it. For each pair, find the length of the unknown side. Okay, so basically what we learned is if two shapes are similar, then fractions made out of their corresponding sides will be equal. They guaranteed me that these two things are similar. So what I'm going to do here is I'm going to make fractions out of the corresponding sides. So let me make a fraction out of the first shape, the big shape. The relationship of this shape's, I don't even know what to call this, slant height. You know, I don't have an official name for it, but this slanted piece to this shorter base piece is 25:10. I can still see kind of this same relationship in the other shape, even if I don't know the names of these things. Can you see that those are the two corresponding sides there? It should visually look like the same angle. So that's what you would spend all that time if you were in a geometry class looking at, proving that shapes were similar, which I'm kind of glossing right over, which is not really that fair to you guys, except for I don't want to spend 3 weeks doing something that will never come up on your test. Okay. But I'm kind of glossing over the fact that angles would be the same. And so I can see that that's that same shape of an angle, even though the side lengths aren't the same. Okay. Similarity retains angle measurements. Okay, so anyway, that's how I know that we have those corresponding sides there. So now I'm going to set up a fraction out of my other one. Now I'll make sure that the side that matched this 25, so the other slanted side, is the unknown. That one's on top. I'll use a letter for the unknown. And since I had the 10 on the bottom, this little piece here, I'll have the 2 on the bottom here. I'm making sure the corresponding sides line up so I have the same relationship. I'm just taking note of what I said. Angles are the same in similar shapes. Again, I'm really, really glossing over a deep subject that a geometry teacher would be ashamed of me right now for not doing this for months and months like they like to. But like I said, this kind of geometry is not on the GED, so we just have to understand that they're like blow-ups of each other to be able to do these problems that are the style that's on the GED. Now I have a proportion problem set up, so now I can solve. Now it's not geometry anymore, now it's algebra. The second I wrote a proportion, I've got an algebraic equation to solve. Anybody remember the wonderful trick that I used to get rid of fractions right from the start here?
Cross multiply?
Exactly. I can cross multiply. And why can I do that? Because I know that things that are in proportion, their cross products are equivalent. So I'll find the first cross product. 10 times x is 10x. And that rule that I just stated, that cross products are equals, guarantees that whatever cross product I got from one cross will be equal to the other cross. And we'll do that. 25 times 2. 25 times 2 is 50. And now it's not a proportion problem anymore. Now it's just a simple little one-step equation. My goal is to get x alone. The opposite of multiplying 10 by x is dividing. So I will get rid of that. I will do it to both sides since it's a change I'm choosing to make. I want to keep my balance. Multiplying by 10, dividing by 10 cancels. X is alone. And I find out that that missing side length is 5. Now, I have to say that this is not the only way to solve this problem. Some students say, Kate, I knew it was 5 before you set up your proportion. And I'm like, that's nifty. That's really cool. Does anybody see the relationship here between the big shape? I don't know what kind of shape it is. I'll just call it a quadrilateral. That's a generic word that means four-sided shape. Okay, quadrilateral, 4 sides. Okay, so can you guys see the relationship between the big shape and the small shape? Some people notice, hey, Kate, look, it's 5 times as big. And so they don't have to do the proportion work. They go, oh, look, well, if 2 got multiplied by 5, then 5 times 5 is 25. Oh, my goodness, that must be a 5. And they just see it. And if you do, you're a blessed person. But it doesn't mean you don't need to learn proportions. This is the kind of back and forth struggle I have with my students. Sometimes they're like, this is easy work. I don't need to do any of your stinking algebra, miss. I don't need you. Now, I dare you to try that method on B. Good luck telling me what the relationship is between these corresponding sides. It's not always as clear. Okay, so when the numbers get bigger, when the numbers get uglier, the relationship will not always be as clear. Now on B, it's not as bad. Some people might be able to see the relationship between the small and the big. If that's you, good for you. But anyway, I can always do a proportion, okay? So first of all, we see here that this is like the longer side of this rectangle, and this is the shorter. And again, I see the longer side and the shorter. So I'll make sure that those line up when I make my fractions. So I'll do the longer side over the shorter here. Guys, did I have to do my fraction like that? No, I could have done it the other way. It doesn't matter as long as they line up, okay? But because I did the longer side on top before, I'm going to put the longer side of this rectangle up on top. You cool with that? Yeah. And the shorter one on the bottom. And whatever relationship I choose to talk about, I'm going to keep the 2 relationships the same, so it really will be in proportion. Okay, so I'll cross multiply to solve, and I'll go start going a little faster because I think you guys got this concept. 105 times x is 105x. 35 times 63 is disgusting. Bust out a TI and hook me up. I got 2,205. Now this is just a one-step equation. Easy, easy. To solve this sucker, all I'd have to do is divide both sides by 105, divide both sides by 105, and I get x is something not as bad as it was before, 21. And of course, it would be 21 centimeters. I forgot to put my unit on my last one, didn't I, guys? And no one even scolded me. You guys are so sweet. Should have been 5 inches there. So don't get intimidated if the numbers get ugly. It's a decimal. It could still be easy, though. But I did try to throw a few more numbers at you to see if I could confuse you with which fraction to set up. So with C, I have a lot of different fractions I can set up, okay? You can see that I have like this side, and this side. You only need 2 numbers to make a ratio. You only need 2 numbers in a fraction. So which 2 should I use? You should use whichever 2 you have going on the other side here. So I have 2.4 and M, and you can see that 2.4 and M are kind of around that big angle, that big obtuse angle right there. So I'll make sure I use the 2 around that big obtuse angle here. Big wide open angle, okay? So I will make sure that my 2.4 lines up with my 3.2 and my M lines up with my 4. Is anybody mad at me for that?
No.
Yeah, it's easy when the shapes are oriented the same way to see corresponding sides. We'll have some later where they get flipped. It'll be harder to see, but right here, pretty good. Okay, so we will cross multiply here to solve, and I didn't leave myself enough room, so I'll just do this to the side. 3.2 times M is 3.2M. And 2.4 times 4 is 9.6. How would I solve something like this?
Don't you just take 3.2 and divide it?
Exactly. Right now, 3.2 is multiplying with M. The opposite of multiplying is dividing. And I'll get M is equal to, I think it's just 3. That looks nice. Ha! M is equal to 3, so that little length there that I'm missing will just be 3 millimeters. Pretty simple, right? Pretty simple. How could it get any trickier? Yeah, let me get trickier now. You know, such a math teacher, such a math teacher. And it's punishment for all those students who don't finish my videos, right? You just watch the first problem, let the GED trick you. Okay. Okay. I have a funny one. Do you see why it's funny, y'all? Look at D.
Because you didn't label P.
Yeah, looks scary. But here's the good news. Even though I have two things I don't know, I don't know two of the sides. Some people say I can't use proportions if I don't know two of the sides. You still can, because I know the relationship between those. They both use the same letter. One's a P and one's 6 more than P. It's that same letter. So I'll still be able to set up a fraction, okay, guys? I didn't really give myself enough space on this page, but I'll set up a proportion using the ratio from my first triangle, P over P plus 6. And we can see this little angle is the one I'm around right here. I'm gonna make sure I'm around the same angle. And so this other fraction that I'm equal to will be 5 over 8. Are you cool with that?
Yes.
So it doesn't make the geometry any harder, but it will make my algebra more challenging that I have more P's going on. Okay, but we can still do this. We are capable of this. We looked at this last class. Let's look at it again. What are we going to get here? Well, we're just going to get more complicated algebra. Let's take a look. First step is always the same. We can always cross multiply to get rid of fractions. So they both have a P, so who cares where I start? 8 times P is 8P, and I didn't give you guys enough space, so I'm just writing down here. Sorry. Is anybody mad at me for that? That makes sense, right? 8 times P is 8P? Okay. Now the other part is the tricky part. This is 5 times all of this P plus 6. And if you remember, this is what Bianca was getting a little mad at me for last time. And Bianca, I left your brilliant questions in the video last time because they were so good. They were so good. I think that's exactly what all students wonder. How come you do that, Kate? So this is the same as 5 times the quantity P plus 6. And I'm just going to write it down before I deal with it. Is everybody okay with that?
Sure. Yes.
Okay. Now, I can't just divide away that little 5 like we were doing last time. So sometimes I have to know another way. Why? Because 8P is not going to divide nicely by 5. Getting rid of that 5 would make things uglier and introduce fractions. So I really am going to multiply 5 times all of P plus 6. Now remember, and I'll write it up here on the top so you can see what I'm doing. If I say I'm taking P plus 6 5 times, it literally means that P plus 6 is happening, that whole thing, 5 times. And of course, if I did that, I would end up with a total of 1, 2, 3, 4, 5 P's. And so you multiply the 5 times the P and get 5 P's. But I would also end up adding 6 5 times. So that's 6, 12, 18, 24, 30 is what I would end up adding in the end if I added 6 5 times. And so you also multiply the 5 times the 6. Multiplication passes out over parentheses. It's known as the distributive property. Now this is a little gross. This is more advanced algebra, but this is the kind of algebra you often see on the GED, so it's good practice. Can you guys see that there is a P on both sides of my equation?
Yes.
How in the world could I ever get P alone if P is everywhere? You have got to pick a side for P before you can even think about isolating him. And so what I'm going to do is I'm going to get all those P's over to one side. I will do it, and this is not the only way, by subtracting 5P. Now, a lot of students ask me a really good question right here. They say, how come you didn't divide? Okay, the reason why I didn't divide is I'm not trying to separate the 5 and the P. I'm trying to take that entire 5P away, and that 5P is adding with 30. Can you see that? And so it has to be taken away through subtraction. Is everybody cool with that?
Yes.
Okay, so let's give that a try. If I have 8 P's and I take away 5 of them, I'll have 3 P's left. And that's equal to, on this side, 5P and minusing 5P cancel, so that I have 3P is equal to 30. And I'm just going to come over here and rewrite it since I ran out of room. 3P is equal to 30. And now this is a one-step equation that I can solve. I can solve this through division. I divide both by 3, and I get P equals 10. So how could it get more complex? The algebra could get more complex. Totally legit. This is, I would not be the least bit surprised if the GED did it, and 99% of GED students just practice the easy proportion problems, never ever graduate to one of these and go, oh crap. This is harder than what my teacher taught me. The only other trick I have in my basket is to flip shapes around. So if you, like me, are not a visual person, you will find this challenging. My husband is a lovely, fabulous, fantastic engineer, and he can just picture things mentally rotating in space. He can look at a 2D diagram and see 3D shapes. And I'm like, I don't know how the heck you do that. This is really challenging for me to imagine things rotating. But some people think it's so easy and don't know what I'm whining about. So let's go take a look. Number 2 says each of the pairs of figures below is similar. For each pair, find the length of the unknown side to the nearest hundredth. Now, I guarantee you that they're similar. So we can set up fractions. The hard part is you have to have your fractions from corresponding sides. And when things get rotated in space, it's not always so easy to tell what the corresponding sides are. Okay, now obviously I'm around this same kind of size of angle. I can see that angle measurement there. Okay, but things can get flipped, rotated, which side lines up with which side. So taking a look at this 23 meters, which side on the other rectangle would you say corresponds to the 23 meters?
R.
What makes you guys say that? I agree with you, by the way. I'm just curious of your rationale.
It just looks similar.
It looks similar. I would call it a length thing. Probably out of the two, that's definitely the longer side on both of them. That can help us. Again, if I was your geometry teacher, I'd take you through so much time so you would know exactly, but most of the time you don't need it. Most of the time you could tell by looking at it. It's kind of obvious which one's the corresponding side, right? And that's usually the kind on the GED. Okay, fair enough? Okay, so then I would say yes, that the 7 corresponds with this 5 there. So beautiful, let's go ahead and set that up. 23 is to 7 as what?
As R is to 5?
I absolutely agree. As the long side of the other triangle is to that shorter side. I mean, really. Now we'll cross multiply. This one's easy. 7R is equal to 115. I am going to solve for R by dividing by 7. Divide by 7. Now, if you go to put that in your calculator, 115 divided by 7, it didn't work out this time. So, I got a decimal, and we know decimals are only one way to express pieces and parts of numbers. You can use decimals or you can use fractions. So I would like you guys to go hunting for clues in my problem. What kind of answer would they like from me?
The nearest hundredth.
Yeah, that tells me that I should do a decimal answer, and I'm going to round it to 2 decimal places. So let me bust out this decimal that they gave me. I'll pull an extra place for rounding purposes. I have it to the tenths, hundredths, thousandths here so that I can consider the number I'm about to throw away. Is that guy big enough to matter? Am I halfway through my digit system yet?
Yes.
I sure am. So I'm actually closer to 16.43 than I was to 16.42. I'll call that 16.43 and 16.43 what? 16.43 meters. B is interesting again, because if you read the directions that I had here, each of the pairs of figures below is similar. And then it says for each pair, find the length of the unknown side to the nearest hundredth.
Mm-hmm.
Interesting on this one because I have 2 unknown sides. Do you see it?
Yes.
So I'm going to have 2 answers, okay, guys? 2 things I don't know, two answers. But let me start by just finding M. That's always the place to start here. So I will set up a proportion. I say M is to the 2M plus 5 side as, what's the corresponding side with M?
17.
17. Bianca, how'd you know? I didn't even teach you anything, Jack, about corresponding sides.
Honestly, it's a guess.
Well, you're right. It's because visually they're the short one. Of course, you know what I mean? Like,
yes.
We have enough visual clues here that we can tell pretty confidently that 17 corresponds with M. And then the long side here, 2M plus 5, should correspond to the long side here, 42. If you set up the ratio wrong, by the way, you guys would know it because you'd get out an answer at some point. You could get out an answer that just didn't make sense. Like you'd get such a weird number. You'd go, oh my goodness, like you could get a negative and you'd be going, why is it negative? Yeah, something went awry. We can't have negative measurements in geometry. It just doesn't make sense. I have my proportion set up. You guys cool with my proportion?
Yes.
Yeah.
Okay, so now let's cross multiply. So M times 42 is, of course, 42M. And on this side, 17 times 2m plus 5 takes a little bit of work. I will write it out so I can take a step to do it. 17 times all of the quantity of 2m plus 5. Mathematicians use parentheses when they want to multiply a number times a quantity, always. You cannot just use a times sign. Is everybody cool with that?
Yes.
Yes.
Okay. So now I have 42m on this side, and I'm going to pass out multiplication because I proved it to you, I hope, last time. I'm not going to write 2m plus 5 17 times, guys, because y'all, I'm a mathematician. And I'm too lazy. Okay. But I hope I proved it next time. So last time. So if I had 2m 17 times, I would end up with 34 m's. Again, if I had 2 m's repeated 17 times, I would have 34 m's. A lot of flipping m's. Too many for this page. Okay. Now, if I had added 5 17 times, I would end up adding 5 times 17, or what is that? 85? Yeah, 85. Okay, brilliant. Okay, so now you can see that I have a more complex algebraic equation than I've seen in some of the other problems. And do you see my issue?
Yes, you have m's on each side.
M's on both sides. First thing I need to get, I got to get rid of that. I can't have m's on both sides. So I'm going to get all my m's to the same side. So I will subtract 34m right here. Subtract 34m from both sides. You guys understand why I'm subtracting and not dividing?
I don't.
Yeah. So Bianca, if I just had a 34m, and like, I don't know, say it says it equaled to 196, and I wanted to break up the 34 and the m. The 34 and the m are shoved together, so they are multiplying, so I would divide. Does that make sense?
Right, yes.
Yes. But on this problem, I'm not trying to break up the 34 and the m. I'm trying to take this entire 34m away. And look what that entire 35m is doing with 85. It's adding. So I'm going to do the opposite. It's a term. It's something adding or subtracting. So I have to move it through addition or subtraction because I'm taking the whole thing, not just the multiplier.
What if you then, instead of doing it that way, took 42m and then divided it?
Oh, I could. Yeah. The nice thing about algebra, Bianca, is that you can do whatever you want as long as you do it to both sides.
Sure.
I could take 42 and divide it. If I did, I'd have to pass out division. Division passes out, and it would just get really ugly. I would just end up with a stupid, ugly, gross statement. These are not nice numbers. And it didn't make my life any easier. I still have m's on both sides. So it's totally legit and totally legal, but it's just messy and not wise.
Okay.
It doesn't get me where I wanted to go. So it would be better to get all the m's together first before you start dividing. It won't get all ugly and fraction and funky and funny. Does that make sense?
Yes.
Okay. So good question, because I've been telling you guys you can do whatever you want. You can. It's just sometimes the consequences of doing, isn't that just like life? Sometimes the consequences of doing whatever you want are messy. So it helps to have wisdom to balance out the power to do whatever you want. Okay, I feel like that's a mother lesson. I'm going to go home and teach that to my teenagers. You know? Okay, so 32m, oh no, I'm sorry. I'm looking at this right here. 42m minus 42m minus 34m. If I had 42 of something and I took away 34 of them, I'd end up with 8 of that something. So I have 8m. Cool?
Mm-hmm. Yes.
And on this side, 34m, if I subtract them out, it zeroes out. So all I have left is a plus 85 or just an 85, positive 85. And now I can solve, and not only would it be good to divide here, I mean, not only is it legal to divide here, it's also wise. I'm just dividing by one number. My m's already alone, my m's already on one side of the equation is going to give me an answer this time rather than a big, ugly, gross expression. So 85 divided by 8 gives me 10.625. Are we cool?
Yes.
Yep.
Okay. Are we done?
No.
No. Bianca says no. Bianca, well, how come I'm not done?
Because we need to round to the nearest hundredth.
How much would it suck to do all your geometry right, all your algebra right? You did all the hard ninja math right, and you forgot they told you to round. Man, that would suck. Okay. So I'll round to the nearest hundredth, meaning after 2 decimal places. Is that guy big enough to matter?
Yes.
Is he halfway? Yes, at 5. We're halfway through our digit system. We'll bump ourselves up. So I'm going to call that about 10.63 inches long for M. Is everybody cool with that?
Yes.
Yes.
Okay, but then something interesting happens. M is not my only unknown, is it?
No.
I have another side I don't know. 2m plus 5. And students just throw up their hands. How in the world am I going to figure out 2m plus 5? And I'm like, y'all, you know what m is. M is not a mystery. You just figured out what m is. What is m?
10.63.
10.63. What does 2m plus 5 mean? It means take m, multiply it by 2, and then add 5. We can do that. We can go and take 2m and add 5 to it. What we're going to do here is we're going to put in a 10 point, and I'll use the original number, 625, in my equation just to make sure that my math is as accurate as possible, as long as possible. But I just plugged in my m right there so I can figure out what the other side is equal to. Is anybody?
Why are we doing 10.625 when we're supposed to be doing 10.63?
That's a good question. Serenity, I'm probably going to get the same answer either way. It's because
Okay.
I'm an anal retentive mathematician. I know that the earlier I round in my work, the more likely I am to lose information. And so even though I'll give a final rounded answer, I don't like to do calculations with rounded answers because I could lose a little bit of data. Do you remember when we were doing those big volume problems and we used 3.14 and our answers didn't quite match Kuta because they used all the digits of pi, 3.14159? We did good rounding, but our answers didn't quite match. Why? Because we used a rounded number and they didn't. So whenever possible in calculations, I like to use non-rounded numbers, even if I'll round them in the final answer. Does that make sense?
Yeah.
Okay, good.
On this one, how would we know that it's it's missing two sides? Like where's the indicator that we have more work to do?
Yeah, and if you can't tell in my directions, it might be because I wrote this worksheet and I didn't write my directions well enough. But I meant to say that when I said for each pair, find the length of the unknown side. Those are both unknown. But the nice thing is you would know very clearly if it was on the GED because there would either be 2 blanks, you know, like m equals and 2m plus 5 equals, there would be 2 blanks for you to fill in, or there would be 2 answers in the multiple choices. So the good news is it'll be definitely clear on the GED, even if you don't like my directions this time.
Okay.
But yeah, they're both unknown. So that's what I was trying to say. I apologize if it wasn't clear. Okay. But that is a good question. Okay. Are we cool with that?
Yes.
Okay, wonderful. So I will now find this other side. So you can plug this entire expression, since it has no letters in it, into your calculator, and I will because I'm lazy. 2 times 10.65 plus 5 equals 26.25. And so how long is my other side? Oh, it's 26.25. Serenity, if you'd have used a rounded number up there in your calculation, you'd have a slightly different answer. You'd have like 26. Well, I don't know. Let's try it. 26.26. See, so close, but just a little different because of that rounding affecting my final answer. This is probably pretty complex. The likelihood is you will actually they do like complex similarity problems on the GED, but the complexity tends to be in word problem form. So I'm going to do one more like this, but then we're going to go look at some word problems, okay? More often you'll see word problems than the complex algebra here, okay? But it could come up. It's fair game, okay? I just want you guys not to panic when you see too much information. You're like, what information do I use? Just the stuff you need. Just the stuff you need, okay? The GED loves to sideswipe you with information. It might not be necessarily in this context, but Serenity's seen it. They'll give you this much stinking information, and all you needed was that number and that number, you know? So we got to not panic. Okay, so this says the quadrilaterals are similar. Again, quadrilateral is just a generic word for 4-sided shape, but we know that similar means that their sides are in proportion. And I want you to find X. This one's hard to set up, especially since I deprived you guys of a month worth of proving that shapes were similar.
Is it
Okay.
7?
What was that?
Is it 7? Like all the numbers, like if you rotate the second one, they all multiply by 7 to get to the other number.
They seem like, oh, so she's looking at corresponding sides. So when she pictured it rotating, were you picturing 3 lining up with 21?
Yes, so 3 times
And
7.
4
Right,
lining up with 28.
right.
And
then
12 with
times-
84. And dear Lord, Bianca said, oh, it's 7 times as big. Oh, it's 7 times as big. And I agree with you that these things are all 7 times as big, but that wouldn't make X 7. That would make X whatever number you have to multiply 7 by to get to 91.
Wouldn't we divide then?
You could. You could. And you're the lucky snot who sees it, Bianca. You lucky thing, you don't necessarily need the proportions. So Bianca thinks she thinks, well, what, can't I just take 91, divide by 7, and save myself a lot of flipping work, Kate? If you did, you'd get 13. I'm going to check it with proportions and see if I get the same thing as you. Okay, Bianca?
Okay, deal.
Okay, fair. Let's set it up. So I'm going to have an X definitely in the proportion that I set up for my small quadrilateral. Because I need to know X, I better have a fraction with X. Now you might be thinking, well, what other side should I use? And actually, as it turns out, it doesn't matter. As long as you can see the corresponding side, set up the fraction with corresponding sides, it doesn't matter. So if you want, you can use the X with the 4. Is that cool? The important part here is that I line X up with his corresponding side. So let's take a look here. Let's start with the side that corresponds with 4, because I think that one's easier to tell. Obviously, the 4 is one of the 2 short sides, so I'm looking for one of these 2 numbers, but which one?
I think 28.
You're absolutely right. It's the 28. It's the longer of the 2 short sides. So they'll retain that relationship to each other in length. So very nice. Okay, cool. Now, which side then lines up with X?
91.
Yes, absolutely. Also the visually longer side, but a little harder to tell. Is everybody else okay with the fact that 91 corresponds to X? Bianca is like my husband. She can do a mental rotation. Now, I've done this enough times because I'm a flippin' math teacher and I used to be a geometry teacher that I don't find this as much of a struggle anymore. But I used to have to trace the shape on a piece of paper and rotate it around and flip it over to see corresponding sides. So if that is you and you can't see it, pause the video right now or take some time after class, put a piece of paper, trace that shape, flip it over and see how those sides correspond. Because not everybody is so blessed to be able to do mental rotations like Bianca and my husband. Okay. And that is actually the only math skill that they can prove that women are weaker at than men, doing mental rotations. In every other way, there's absolutely no significant difference between men's brains and women's brains in math, but apparently that's just the one. It doesn't mean every woman does, but as a majority, we tend to struggle with it more than men do. Anyway, I just think it's interesting. Okay.
I do have a quick question.
Yes, ma'am.
Why are we doing X over 4 when they're on the same shape? Shouldn't it correspond with the shape we're trying to find its proportion to?
So the good news is, as long as your relationships work, you can set up any fraction you want. You just have to keep the fraction the same. So Bianca, you wanted me to do like X with the 91, since X corresponded to the 91.
Right.
And then line that up with 4 corresponding with the 28.
Yeah.
Those 2 proportions are both have the same relationship from top to bottom. So it absolutely doesn't matter which one you use. You'll get the same answer.
Okay.
Okay. So don't like wipe your brow if you thought that was a big deal. It's not. Just the important thing is that I'm consistent in my relationship. So I chose to do small quadrilateral, large quadrilateral when I was looking at either side. And then I chose to do corresponding sides this way. You're choosing to do corresponding sides with corresponding sides and small quadrilateral on top, big quadrilateral on the bottom. You know, but you still kept your relationship consistent, so you'll still get a good answer out of it. Make sense? Okay. So let me erase now all those circlings I've done. Man, technology rocks sometimes when I can work it. Okay, let's solve this sucker. So X times 28 is 28X. And 4 times 91 is 364. Can I just do something really good since Bianca asked me that question? Bianca, I want you to imagine that you did the same cross multiplication on yours.
Okay.
28 times x would give you 28 times x, and it might be in a different place, but look at that. 4 and 91 will give you
364.
Yeah, we set up the same proportion. You thought about it a little differently than I did, but that's really the same relationship. See how we got the same thing out of it?
Yes.
Okay, cool. Okay. Anyway, I'll solve mine now. These 28 and x are multiplying, so the opposite of multiplying is dividing. And I'll get x is equal to. And Bianca, I love your questions because you ask the questions everybody else in math class is afraid to ask. The GED teacher always assumes you guys that we're such brilliant, brilliant teachers that you walk away understanding everything we say. And then we go and you guys bring back your homework and we're like, oh, never mind, we didn't teach that well. Anyway, so I just got that x is 13. 13 what? I don't know. There were no units on my shape. 13 some kind of unit. And Bianca says, of course it made sense. I did it without all your algebra. So I say, once again, if you can do it without algebra, you're the blessed one. But have that algebra as a backup for when the numbers aren't so easy to see, like in some of the problems we did. The most famous similar shape problem ever. When I taught math in high school, I did teach high school math. My favorite people are always the people who say, I don't understand any math, because it's like a challenge for me. I'm like, oh, none, huh? Let's see if we can make some of it make sense, you know? And so I would take, the day we did this activity, I would take my entire class outside and we were roaming around campus like hooligans, which was good because we were like the low, slow, back of the school portable class, you know, the ones who usually don't get math. We had a lot of fun. But anyway, we went out and we measured everybody's shadows so that we could figure out the height of everything on campus. So let's take a look at this. Number 4. It says a 6-foot tall man casts a 7-foot shadow. If a nearby tree is casting a 26-foot shadow, how tall is the tree to the nearest foot? And students go, I don't flippin' know. How the heck am I supposed to know, Kate? Draw me a picture, please. Think about this. If you have a 6-foot tall man right here, he's 6 foot high, and he casts a 7-foot shadow, his shadow falls along the ground like that, doesn't it? Now, how is a shadow made? What is a shadow made from?
You blocking light.
You blocking light. There is light coming down from the sun. Does that look like a shape to you?
Mm-hmm.
That's a right triangle. I'm standing up straight. I don't lean over to measure my height. I'm standing up straight. I'm making a shadow from the angle of the sun. Okay? Now you got a tree that's outside. Okay, so, and I say it's nearby, okay? That's important that the tree is nearby, because if the tree is nearby, the angle of the sun is going to be the same. We're going to have those same angles. So here I have this tree. I don't know how flippin' high the tree is. Why? Because I can't get up that high to measure it. I got a desk when I was a high school teacher. I got some books, but nobody gave me a ladder. I could not get to that top of the tree to measure it. But you know what? I could go along the ground and measure the tree's shadow, couldn't I? The tree's shadow, we said, was 26 feet. Now, if the tree is nearby to the man, the sun is going to be at the same angle, meaning I just created similar right triangles. Now, I don't know how high the tree is, but I have enough information to figure it out. The relationship of the man to his shadow is going to be the same as the relationship of the tree to its shadow. So the relationship of the man's height to his shadow is going to be equal to the relationship of the tree's height, I don't know it, to its shadow. The probably most famous application of similar shapes, it is a favorite. I wouldn't be the least bit surprised if you saw it on the GED. Math teachers use it all the time too, because we're trying to think of a time in life that a similar shape would always come up. This is one of those. Okay, is anybody mad at me?
Mm-mm.
Now it's easy to solve. 7 times h is 7h. 6 times 26 is 156. Divide both sides by 7. And as so often happens in the real world, my answer is not pretty. Why? Because God does not go out there and say all tree heights must be whole numbers. Sorry, Real world doesn't always work out as well as the problems that the math teacher writes. Okay, so we should round as necessary. Did they give us any rounding directions?
Nearest foot.
To the nearest foot. Now remember that anytime you're at a nearest unit, you want to cut it at the decimal place. I'll cut it right there. Examine the number I'm about to throw away. It is not big enough to matter. I'll call that tree about 22 feet high. And we literally figured out the height of every building on campus, every flagpole, everything. We were running all over campus the day we did that in my math class. I'm sorry, y'all are on a computer. We can't do it. We would have fun, though, if we did. The college would wonder what we were up to. Okay, is anybody mad at me?
A little bit.
Yeah, why are you mad at me?
Because if a 6-foot man casts a 7-foot shadow, so it's a foot taller than him when I was first reading this, right? And I felt like if we were doing like a proportion, then a 6-foot tree or 26-foot tree, wouldn't their shadow be bigger?
It is. It is. 22-foot tree, the shadow of 26 feet is bigger.
Oh, yes, you're right. Sorry.
Did you have the numbers flipped around?
Okay, yeah, I read it wrong. So
okay.
Comprehension is key here.
Yep, so I see my 22, and I see the shadow a little bit longer than the height in both cases. That's a very good check, Bianca. If I had gotten a number that it didn't line up, like the shadow was suddenly smaller than the tree where it used to be larger, you should be really blinking your eyes like, that's not in proportion. I did something wrong.
Okay.
So you did the right check, even if you did kind of like switch it a little bit.
Okay.
This also comes up in map making, topography, and construction industry because why? They don't use real life representations of the sizes of things. You know, I'm building an extension on my house right now. We got blessed with even more foster daughters than we expected, so we need room. So we are building an extension right now. You know, I cannot get a piece of paper that's as big as the bedrooms we are building. That would be a big piece of paper. And so what do? We shrink those plans down on a piece of paper, but we keep them to scale. We keep them in proportion. Does that make sense? And so we see proportions showing up in maps or in blueprints or building plans. Okay, so let's look at number 5. It says a map has a scale of 2.5 centimeters to 20 kilometers. So 2.5 right there, that is a relationship. I can feel free to make a fraction out of it. Now notice that I have the centimeters on the top, the kilometers on the bottom, and these are the numbers that are on my map scale. Okay, now let's come on to the other side, and we're comparing two towns, Riverside and Smithville. Riverside and Smithville are 18 centimeters apart on the map. Where should I put my 18 centimeters?
On top.
On top. Centimeters should line up with centimeters. And then we're asking then how far apart are they? I want to know their distance from each other. So kilometers is a distance measurement. This is the thing I don't know, the real kilometers of these two very real towns. And now I can cross multiply to self. 2.5 times m is 2.5 m. 18 times 20 is 360. And I can divide by 2.5. I totally, spoiler alert, a lot of people have come to me now. You're not supposed to talk about what's on the GED test, but a lot of people have come to talk to me about this, something about a blueprint bridge. They're like, oh, there's a blueprint, there's a bridge. So I'm not telling you what's on the test, but I would expect if it was anything about a blueprint, it's the same concept of shrinking down and getting larger. Does that make sense?
Yeah.
Yes.
Okay, so 360 divided by 2.5 is 144. So how far apart are these towns in reality? 144 kilometers. I make sure that my unit lines up. Whatever I was looking for should line up here with that relationship. I did kilometers to kilometers. Now, another industry that uses this, it's not just people running around in their backyard measuring shadows. See, like, how useful is that actually? So surveyors actually use this as well. Now, you guys have to apologize for this fact that I could not find any good free graphics for this in Creative Commons. So I had to create my own graphic, and I am a much better algebra teacher than I am a graphic designer. So here is my very ugly picture of a lake. yeah, a surveyor wants to measure the distance across a lake. So, you know, how am I going to get across the lake to measure the distance? Am I going to like have my friend on one side of the lake hold a measuring tape and then I'm just going to paddle across the lake? You know, there's not a really good effective way to measure across water. But what surveyors will do is they'll draw right triangles with the same angles so that they can measure a smaller right triangle to figure out the dimensions of a larger one. Does that make sense?
No.
So did you say no, Bianca?
No, yeah. Well, because it's not, I mean, lakes aren't even in a right.
No. But I can still go from one point across the lake to the other if I wanted to find like the distance from here to here. I know that it won't be the same distance at every point, but if I do want to find this missing distance here, what I could do is I could draw a right triangle. Now look what I did, Bianca. I drew from a point on land to a point on land. See how all my endpoints are on land?
Yes.
So I can walk that. I don't have to like boat across or something.
Right.
Okay, so from here to here, you know, you could figure out, even if I can't go all the way across this big body of water, okay? And now this little guy is drawn entirely on water. And as long as I make sure my angles are the same, that's what a surveyor would do. I promise they have special equipment just to do that. As long as I make sure my angles are the same, my thing is gonna be in proportion. And so I'll be able to figure out that long missing length across the water. Does that make sense?
Yes.
Okay, beautiful. So let's set up a proportion. Now I will do, you know, my small triangle on one side and my big on the other. Again, it doesn't really matter if you do corresponding sides across her, but I just like to do one shape at a time. So I have this 80-foot side to this 120-foot side of the small triangle. But now when I look at the big one, you know, I only have one number, 532. Which one does it correspond to? The 80 or the 120?
120.
Yeah, no, you say no?
Mm-mm.
And this is really where we're at a disadvantage since I didn't teach you everything about similar sides. The only trick at our disposal is looking at the length of those two. So between 80 and 120, which one is bigger?
120.
120. So this is the big side of this triangle. I'll call it long and short so we don't mix up small and big triangle. Now look at the other one. Of the two, visually, which appears longer and which is shorter? Is it too hard to tell? I'm looking at this big triangle now. Of these two sides, this one, the one I have a question mark and the one I have 532 on, which one appears longer?
I think the question mark.
The question mark. And the other one appears shorter. So I'm going to make sure that my short 80 lines up with my short 532 and my long 120 lines up with my long unknown. And that's really where you could go awry and really where I've done you a disservice by not doing similar shapes for a month. Yeah, because the only tool at our disposal is like what looks, the relationships to the sides, what they look like. Let's multiply through to solve. 80 times x is 80x. 532 times 120 is not something I'm trying to do in my head. 63,840. Divide by 80 to solve. Divide by 80 to solve. And x is equal to 798. And once again, you should do a visual check. You know, does it look like that number makes sense? In case I had set up my proportion wrong, I was expecting that thing to be longer. And did it really end up longer than the other side? It sure did. So I'm probably safe. I have 798 feet across that lake. Here is my best job to recreate this bridge problem that I imagine that they're probably talking about. Since they talk to me about blueprints or scale drawings, this is probably what they're saying here. And they are right. I totally, before I was a GED teacher, I think I've told you guys before, I was a tutor to adults with disabilities, but I tutored in every industry you can think of. And one of the things that I did was construction trade. And we did problems like this all the time. So number 7, the scale drawing of a bridge. So here we have, I don't know, a bridge. I'm not a good artist. It's 3¼ inches high. And, oh, it's a very short bridge. I was not expecting that. Sorry, I'm just redoing my drawing based on the numbers now. So apparently it's a very tall bridge, 3¼ inches high, and it's only 2½ inches long. It's my bridge that kind of looks like a crown. I'm not going to get a new job as an artist anytime soon, y'all.
Yeah.
Now we're going to use this scale drawing and we're going to make a real bridge. There is no real bridge. That's only 3 1/4 inches high. And 2, we're going to have to blow it up, okay? So we are going to make some real bridge in the world, and it's huge probably. But I only know one of its measurements. I know that it's 19.5 feet high. I do not know how long it is. That is what I'm trying to figure out. I can set up a proportion to solve it. Now, you could set it up with fractions, okay? I do not want you to think you could not. You could totally, legitly write 3 1/4, don't write this down, ladies, over 2.5 is equal to 19.5 over some unknown. Could you do this? Yes, and your TI could handle all the work. You could multiply the fractions, divide the gross fractions. You could do it all in your calculator, okay? So don't think this isn't possible. But I don't want to because it's gross and it takes a lot of button pushing and it makes my finger hurt and I'm a lazy mathematician. I see an easier way. You guys, what's an easy way to, do you know an easy way to express these particular fractions? I think you do.
Decimals.
Decimals. Not all fractions express nicely in decimals, but halves and quarters sure do. You guys know all about halves and quarters. And so that is how I would choose to write this. I would choose to write it with decimals. Do you have to? No, you don't. But if you don't, then you're doing math with fractions, either by hand or in your TI. Okay? Fair enough? So I will write, instead of writing 3 1/4, I will write the decimal version of 3 1/4. A quarter is worth how much, guys?
25.
25 cents. So 3 1/4, we call it a quarter for a reason. 3.25. So the relationship of the height of my scale drawing to its length, 2.5. A half is written as what decimal?
2.5.
Exactly. A half is 0.5, like 50 cents is half a dollar. 2.5. Beautiful. And that is going to be equal to, now I see the height. So I will make sure my height corresponds with my height in my proportion. It's 19.5 and I'm too lazy to type in fractions. So I put 19.5. Again, if you had to, you could, okay? It would just take more typing on your TI. And there is my unknown. Is everybody cool with that?
Yes.
Yep.
Okay, so 3.25x is equal to 19.5 times 2.5. Oh, I must have done something wrong. I just got the weirdest decimal I ever saw in my life. Let me try again. 19.5 times 2.5. Ah, there, that makes more sense. 48.75. We all cool? And now the final step here will be to divide by 3.25. Divide by 3.25. Oh, and it came out perfectly. Look at that. I wasn't even expecting that. It's like I planned it. 15 what? 15 what?
Inches?
No feet.
No feet? How come no feet? There were inches in the problem. There were feet in the problem. How do I know what unit I'm in?
Oh.
So that 19.5 on the bridge was in what? The 19.5 on the bridge was in feet.
Feet.
So if this is the relationship between inches and inches on the left-hand side, you know what it's going to be on the right-hand side? The relationship between feet and
Feet.
feet. Exactly. That was like a trick question. I was trying to figure it out. But I'm definitely in 15 feet. And that makes sense because if I had a real-life bridge that was only 15 inches long, I probably could have just stepped over. I don't think I really need a bridge at this point. Okay.
Maybe it's for a Barbie house.
Yeah, it's a Barbie house bridge. Let's let math make sense. I swear it really could. It could be like a miracle and it could actually make sense. Okay, was this my last problem?
Yes.
That's good because I talk too much. Guys, it can't be denied. I know. I was just admitting it to my classroom class today that I talk too much. I was like, of all the things I said today, which things should you pay attention to? This one. Okay. So here are some proportions as they could occur in geometry. You guys didn't seem to struggle with them too much, even when I made the algebra pretty tricky. Next week, what are we going to do? I've actually finished all the geometry that's on the GED, but students make a really bad mistake in that they do this kind of math, and then 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 they go and take their GED, and it's all mixed up math. And then they lose their flipping minds because they're just not prepared to know what to do and when to do what. And so next time what I'm going to do is I'm just going to mix up all the different geometry we've learned. It's going to be a lot of word problems like it'll be on the GED. So we're trying to draw things and interpret what's going on. When do we use the formula sheet? When do we use proportions? When do we use Pythagorean theorem? What are we going to do? Okay, so we'll play that game next week. And it's good for anything you study to always just kind of go back over and look at it when it's all mixed up, to build that skill of what do I do when I'm not sure what to do. Okay. So thank you guys for joining me in class. You know that my favorite thing is not talking to myself. And I do appreciate you. And I will see you next week when we do a mixed geometry review.